All right. So when students ask questions, Chife, can you monitor the chat? Sure. And you interrupt me, and then you read out any questions. All right? Are we live, Buck? Okay. Welcome, everyone, to the very first class of Distributed Systems. We have a great class prepared for you. And I'm actually in the classroom, Rashid Auditorium. There's a whole bunch, 240 empty seats with only 3 people sitting in them. Of course, we hope that this is just for the first 2 weeks of class, and in just a couple of weeks, I'll be able to see you all in person as you're sitting in class. Just for you to see what I look like, I'll take off my mask briefly. My name is Satya. That's the abbreviated version of my full name, Mahadev Satyanarayanan. And I'm teaching this class with a whole team of people who are very excited to be able to teach you this class. So one is my colleague, Babu Pillai. Babu, do you want to say a few words?
Sure. Okay, great. Hello, my name is Babu Pillai. I'm looking forward to teaching you distributed systems this semester. This is my, I think, 5th time teaching with Satya in the spring. So hopefully it'll be a great class, and hopefully we'll see you all in just a couple of weeks. I'll be back later in the program to introduce Project 1.
Thanks, Babu. We also have a great team of TAs, and I want to introduce them to you. The first person is Anup Agarwal. Anup, if you're on Zoom, please introduce yourself.
Hey.
Anup, are you on Zoom? Okay, if Anup is not on Zoom, here's what he said about himself. I'll let you read. I love that little cartoon down below. How hard can distributed systems get? Even grandma can learn how to do distributed systems. So that's Anup. Anup is a PhD student. Our next teaching assistant is Mihir. Mihir, if you're on Zoom, introduce yourself. Okay. Anika Banga. Anika is right here in the classroom. So do you want to come up front, Anika, so people can see you on the video camera? And you can very briefly take off your mask just to show people what you look like.
Hello, this is what I look like. Really excited to work with all of you.
Thank you, Anika. Thank you for making the effort to come to class in person. Chife Dong. Chife is also here. Chife, please come and introduce yourself.
So, hi everybody, I'm Chife, and it's a pleasure to be the head TA this semester. Really excited to see you all and help you as I can. Welcome to the recitation and office hours. So, enjoy.
Thank you, Chife. Next is Sid Girdar. Sid, are you on Zoom? No, Sid. Lily Hay. Lily? Santanu Kamath.
Hey, everybody.
Yeah. Hi, Santanu, are you there?
Yes, I am. Can you hear me, Prof?
Introduce yourself.
Hey, guys. I'm a master's student at Language Technologies Institute. I'm doing my master's in computational data science. I took the semester last fall and I really enjoyed it. So I'm looking forward to, helping you guys out, and that can be through office hours or stations. Looking forward to seeing you all.
Thank you, Santanu. Chenkai Lee, Chenkai. Chenkai is not on the call, but you can see what he looks like, and that's what he had to say. Jeshi Liu, Jeshi.
Hi, I'm here. Yeah, hi everyone. I just go by Jackie. I'm a senior in CS, and I also took this class last fall. Definitely really enjoyed the content. So yeah, I look forward to working with everyone.
Thank you very much, Jeshi. Rohit Pandey, Rohit. I think Rohit is traveling. Sumant Rao, Sumant.
Hi, Professor. Hi, everyone. My name is Sumant, and I'm a master's student in the Language Technologies Institute. I took the course in the last fall semester, and I fell in love with it. So yeah, I'm excited for the new semesters, and I look forward to interacting with you all. Have a great semester.
Thank you, Sumant. Ashwin Srinivasan. It's taken on the Pausch Bridge, as you can see, very pretty picture. I don't think Ashwin is on Zoom. And last but not least is Clarissa Zhu. Clarissa? I don't think Clarissa is on the call, but these are the TAs for the class. They're very excited to help you. Remember, there were students like you not so long ago, last year or last semester. And so they have a firsthand experience of what it's like to take this course and where the areas are that you might need the most help. So we're looking forward to a great class. I want to take just a couple of minutes to give you the big picture about this course. We're going to be delving into the details for the next 14 weeks, okay? So you're going to be seeing this in great detail, but just once, just for one slide, I want to give you a very high-level overview of what this class is about. If I were to use a metaphor to describe this class, it's this metaphor of a river, which starts out as a tiny little stream in the distance back in the 1960s. The oldest topics about which you will learn in this class, virtual machines and caching, both of them had their first appearance in 1968 and 1969. So that is nearly now 60 years ago, 60 years ago, is when these concepts were first discovered. Now, obviously, they have both undergone unrecognizable amounts of evolution, change, etc. What you see when you think about distributed systems today in 2022, you think of companies like Amazon and cloud computing. You think about Facebook, you think about Google, and so on. If you drill a little deeper, you will see the topics that they work on. Consensus, Paxos, two-phase commit, Byzantine failures, caching, prefetching, all of these concepts. And this whole body of knowledge distilled into a 14-week class is what we're going to learn. Obviously, 60 years of learning distilled into 14 weeks is going to have to be an enormous degree of compression. It's lossy compression, no doubt. But I hope by the end of this class, you'll look at this picture, and I'll show it to you again on the last day of class. Keep this in mind. And you'll see how these ideas that you've learned in this class really both have roots that are very deep and also project into the future. A common theme in this class, and this relates to the previous picture, is that we only study things in this class that have withstood the test of time. And this is important. Let me explain to you why. Okay? The field of distributed systems changes dramatically. It's fast. Okay? If you look at this device I have on the slide, the first version of it appeared in 2013, 8 years ago. An updated version appeared in 2019, just 2 years ago. This is an amazing device. It weighs 36 grams. Okay? Does anyone remember how many ounces that is? It's like less 4 ounces, 3 ounces, 1 ounce. Is that what it is? 36 grams, so maybe 1.5 grams. I think it's 25 grams is something. So 1.5 ounces is what this is, 36 grams. It has a battery, a processor, memory, microphone and speakers, a video camera, a small display, Bluetooth, and Wi-Fi wireless transmitter. All of that in this little. And the compute power of this device is greater than that of this entire mainframe that filled a room. If any of you saw this movie, Hidden Figures, that came out about 5 years ago, they talk about the mainframes and you see pictures of it. So a room-filling computer has been replaced by something that's so light that you can wear it for many hours and not feel a heavy weight on your face. How is it possible? What is the magic that makes this possible? It turns out that crucial to the success of this device is the existence of caches, L1, which is the cache closest to the processor, L2, which is one level further, and L3 even further away. So multi-level caching is a big part of the reason why this works. Now, the idea of caching, the concept behind it, was first demonstrated in this big room-filling machine. And in fact, this photograph at the corner here shows the actual hardware. Notice the person's hand, fingers and hand there. That's the size of the cache that fit into that machine. And one of the optional readings for this class, if you're interested, is this paper, which describes the cache concept from 1968. Okay, so it's pretty mind-boggling that something that was done 60 years ago provides at its heart value 60 years later today. And the question I want you all to think about is, in the time frame in which you graduate and you go off and you're working at Google or Facebook or Amazon or start your own company or Apple, what is going to be important? Google Glass by 2030 is going to look pretty old. Maybe by 2030, the professor who's standing here in Rashid Auditorium telling students about distributed systems will be pointing at Google Glass just the way I showed that big room-filling mainframe and say, those poor people back in 2022, they had to use this thing that we all look at as a museum artifact. Okay? So the question, which is what this class is really trying to focus on, is what can I learn now that'll still be useful to you in 2030? And in fact, hopefully you have a longer career than that, 2040, 2050. Right? So this is the challenge that we face, and it lies in the basis of this class. So the first premise of this class is that technology changes incredibly fast. Okay? And it's going to continue to change. And it's unpredictable. It's not random, but it's unpredictable. The integral is huge, obviously. The derivative is very large and is continuously large, then the integral is also going to be very large. To make matters worse, the world outside also changes. You know, not that long ago, maybe 1980, 1990, even the year 2000, people were not so worried about climate change, for example. Today, if you think about a Facebook data center or an Amazon data center, the first question is, what is the environmental footprint, right? What is it going to do in terms of, you know, CO2, in terms of, in general, the climate change conversation. Similarly, 10 years ago, when you thought of Facebook, people thought of it as primarily a technology for social networking, for people to get together. Today, it has been shown to have huge impact on politics, on many kind of events in the world. So the external context in which all this dramatic change that we're talking about is happening also is large. So in the face of so much that is going to be different, what is the point of this course? Okay? So the point of this course is that in spite of all this change, there are deep principles underlying distributed systems that endure, and that learning these principles is worthwhile. Just the same way it's worth learning Newtonian mechanics, which you learn in Physics 101. Because while cars and aircraft are going to be very different, the physics underlying them doesn't change. And distributed systems, we will emphasize in this class, wherever there's a choice between focusing on highly relevant but current technology versus looking behind and asking why. Why are we doing it this way? What is the problem that it's trying to solve? Why is that problem difficult? What have people thought about? What are the approaches people have used? And why is this the right way? The why is often as important as the how. So that is the shape of this course and the focus of this course. We have a number of resources that we have created for you. The most important is the one that you should always go back to reference, is the course webpage. And it's on the web. And here it is. It tells you about the topics that we will cover, the grading policies, information about the office hours for Babu and me, as well as all the TAs, where to find the slides that we will be using in class, and also course policies on Piazza and so on. So please note that all this information you assume to have read and carefully agreed to as part of taking this course. In particular, I want to emphasize this policy on academic integrity. Needless to say, all courses at Carnegie Mellon assume the students are bound by this policy. But I want to emphasize it. In every class, there are a small number of cases where unfortunately students violate this. And unfortunately, they have bad consequences. So avoid it. Don't go near them. If you're ever in doubt about whether something is okay, talk to one of the TAs. They can guide you. In particular, please keep in mind that we will be using plagiarism detection software to compare your solutions with those available on the web, those available from past years, from former students. So stay away. Don't go anywhere near these hazard lines in your work. Okay. There's an area in AFS, that's the path name in AFS, where files related to the courses, files used by AutoGrader, AutoLab, and the class lecture notes, all of those things can be found there. You'll need to be authenticated to CMU, to en route, to use it. That's where the class notes will be. And of course, all of you know Piazza. That's what we'll be using for questions, answers. The way we think of Piazza is it's an extension of this class. If you were here in person in front of me to ask a question, you would raise your hand. We view asking a question in Piazza as exactly like that. Okay? Now, there's no such thing as a private question on Piazza from this viewpoint. You ask a question, everyone in class can hear you. And notice, there's no such thing as asking an anonymous question. People know who's asking the question. Okay, so we do allow you to be anonymous to other students. It's a small concession we make, but we don't have private questions on Piazza. So use Piazza sparingly. If you were in class, you would not monopolize a large part of a lecture. Similarly, we expect that when you ask questions in Piazza, you have thought through and asking the question after some prior thinking. And the questions you ask are valuable. If it occurred to you, it probably occurred to many other students. They just didn't ask it. So we view the answers we give as not something just for you, but for the whole class. Okay? So that's the way we look at Piazza. And I think that covers everything. I'm going to pause here in case anyone has any questions. Otherwise, I'm going to start our first topic. I'll give a moment. Chife, any questions? Okay. Okay. So we're going to begin the very first topic, which is remote procedure call. And the essential idea behind remote procedure call is to pretend that there are no distributed systems. It's as if this course didn't exist at all. That sounds pretty extreme. Why would people do this? Well, there's a good reason. Remember that river which stretched back in the Stone Age, when we didn't have all the tools for distributed systems that we have today, people had to work with bare hands. And when they tried to create distributed systems, they learned that it was really, really hard. And a big part of the source of difficulty had to do with the fact that there are many moving parts. There's the server over there on the West Coast running. Over here is a client. In between are 100 network routers that are involved in getting your packet from here to there. Some wireless, some fiber network. All of these things have to work perfectly for your distributed systems interaction to actually work. If I actually had to think about this and writing code, I would never write a successful piece of code. So the ability to hide complexity is the primary reason that remote procedure calls were created. People learned by simplifying what is going on, by giving you the illusion that what is happening here is just as if it was running on your laptop or your desktop or your smartphone. If we can make it look like that, I have greatly reduced the complexity. Notice, it doesn't guarantee your code is correct. It's possible to write code for your desktop, which has plenty of bugs. All of you have experienced doing this, right? We all have. So the reason to use remote procedure calls is simplicity and reduction of complexity. How does it do this? After the first generation of distributed systems, the first 10 years or so, people looked at it and said, how do these systems look like? What do they look like? Very, very early in the history of distributed systems, it became clear that the organizing principle was very often that of a server, which abstracted some service, very much like a Java class or a C++ class, right? So it's an abstract data type. You can think of a server as implementing an abstract data type. There's a number of methods, and those methods are how you operate on whatever the data is. And any user of the server is referred to as a client. Now remember, client and server are per interface. You can cascade this. I can have server A being used by client B. Client B can offer a service to client C. So in that relationship, it is acting as a server, and so on, right? So you can have a long chain of this. And so a server-client relationship is a per interface relationship. All of you have studied in previous classes the use of abstract data types in different programming languages, in Java, in C++, and so on. And so here are some examples. If I had a printer, a print spooler, I might have, here's a file, please print it for me. That's Q file. Has my file printed yet? That's checking the file status. Oh no, I didn't really mean to send that 5,000 page document. Please delete my print request. Of course, this delete may or may not work. If you send it too late, 5,000 pages may already have been printed. But maybe you can catch it halfway and only chop half a tree down. Maybe it's only the first 2,000 pages that got printed. The rest of it, you might still be able to save. If I have a file system, creating, deleting files, making new files, copying new value into an old existing file, you will deal with this in this class. All your projects will be centered on file systems. You can imagine lock managers, right? So Google has a lock manager called Chubby. And you can do things like obtain locks, write locks. What is it a lock for? Lock manager doesn't really care. You can make the lock be a lock for anything you want, as long as all the clients agree with the server on what it's for, it works perfectly. Time of day. How does your desktop or your laptop or your smartphone keep time, even though it may drift? The answer is there is a protocol called NTP, Network Time Protocol, and you can use that to synchronize clocks in a distributed system. So these are examples of interfaces in a system. Now, one of the very interesting things about remote procedure call is that I mentioned to you we are simplifying. The main thing we are eliminating is parallelism. We are taking something that is actually parallel and forcing synchrony into it. That sounds pretty stupid. Why would any sane person take events that could actually independently operate and force them to be sequential? Right? That sounds, something seems to be wrong there. The reason people do this is because of bad experience. Very early in the history of distributed systems, people tried to use message passing. They tried to exploit the parallelism. You would send a message, you wouldn't wait for the reply, it would come later, and you would say, oh, this is the reply from message number 12, which I sent half an hour ago. But before that, I've already received the replies from messages 13, 14, 15, 16. It turns out that while you can make this work, the code turns out to be ugly. And ugly code is very difficult to debug, it's very difficult to get right, it's very difficult to maintain, et cetera, et cetera, et cetera. So the reason people give up the parallelism implicitly is because there is a better way to make explicit the parallelism when you need it. The way you do it is to explicitly create a new process through a fork mechanism or a new thread through a thread forking mechanism. And in all other cases, you keep the flow, your purely sequential flow. One huge advantage of doing this is familiarity. All of you in this class have taken courses like 15 to 13, and you've taken many other courses possibly in computer science and programming. Without exception, all of them involve use of procedures. It means you're already familiar. Then you know how they work. You don't need to be taught how to use them. What worked there works in distributed systems. That's a tiny little bit of change, but that's it. We'll look at the changes in just another slide. So the ability to use a familiar paradigm means that your reasoning is simplified, all of your programming experience from previous classes comes into play. Alas, that similarity is not 100%. And therein lies grave danger. Okay, it turns out that there are really two aspects of procedure call that you have to achieve in a remote procedure call. The first involves control flow. The second involves syntax. Project 1, which we'll be handing out today, and Babu is going to talk about it in another 10 minutes or so, is going to be about the second of these two aspects, namely invocation syntax. Somebody said something? Question? Was that an accidental unmute? Okay. If you have a question, feel free to speak up or send a chat message and Chief A will ask me the question. Otherwise, we'll assume that that was just a glitch. Okay, so there are two different aspects, control flow and invocation syntax. Let's go over these individually. In the local case, forget distributed systems. We're just talking here about a C program or a Java program or something. There's a caller, it calls a procedure, and then the caller blocks. Control is transferred to the piece of code that was called. So over there, the callee executes. Who knows how long it might execute? If you have a bug in the code, it could be in a tight loop that never terminates. And that poor caller is stuck, waiting forever. Hopefully, you've written good code, not bad code, so that code actually terminates, and eventually control returns to the caller, which then continues execution. So this notion that when you make a procedure call, you block, no action happens locally while control has been transferred, that metaphor turns out to be very valuable to capture. And so in remote procedure call, you have exactly the same guarantee that the caller has his state frozen while the callee, which is the server, executes, and then control returns, after which the local state may change again. Now notice this is the ideal. In practice, it's very, very difficult to guarantee that local state doesn't change. And some of the hardest bugs in distributed systems happen when in fact this assumption is violated. Behind your back, without your knowledge, a portion of your local state changes that you are not aware of. And therefore, by the time the reply comes, this picture is not true. Okay? In the distributed systems case, assuming you have none of these kinds of bugs, the picture looks almost the same. The only difference, and we will have a lot more to say about this about 2 or 3 classes from now. Notice up there how the dotted line is flat. Here, the dotted line angles downwards. If you assume time flows from the top of the slide towards the bottom, the reason for this is because packets cannot be transmitted instantaneously on the internet. They may be fast, but fast is different from zero. In the local case also, it's not really zero, but it's so close to zero that the approximation is much better. Here, at the speed of light, it takes 16 milliseconds from New York to San Francisco. Speed of light. Now, most real networks don't come anywhere near the speed of light. There's at least a factor of 10, maybe 5. So 60, 70 milliseconds round trip from New York to San Francisco and back is what the sum of the 2 dotted lines is typically in many cases. And so that's large enough. Your laptop or your desktop in 60 milliseconds can do a lot. There can be other processes, other threads that can change local state in those 60 milliseconds. And so a lot of the complexity of distributed systems comes from the fact that while we pretend the dotted line is horizontal, the reality is that the dotted line is at an angle. And the slower the network, if you talked about a robot on Mars, which we have one right now, and you're talking about talking to it from Earth, it takes 8 minutes. That's how steeply angled the dotted line is. So one of the interesting and important cases to consider in distributed systems is where latency, or the time delay of travel, is very substantial. And we'll study that in this class. We won't start with that because it's a hard case. We'll start with simpler cases. So this is the first part of this, the control flow part, emulating this picture with this picture. Invocation syntax, so the programming language typically determines what a procedure call looks like. So this is what it might look like in C. You have some function foo, you have some number of parameters, you provide them. You've studied in previous classes about call by reference, call by value, right? So all of those apply here. In the remote case, in a programming language that is based on C, you typically include an extra parameter, which tells you which of the many servers that could have function foo you wish to talk to. Now, I'm showing it to you this way. Some syntaxes would use cid.y or server name.y. Right? So there are many different syntaxes. The basic idea is you have to disambiguate which one you're referring to. Now, this faking has limitations. We can come close, but we can't do it perfectly. And the single biggest reason that it's not perfect has to do with address space. When I say memory location 1000 in the local case, the calling procedure and the called procedure both are talking about the same memory location. There's no doubt, there's only one computer. There's only one memory address 1000. What's not to understand? In the distributed case, location 1000 in memory on the client is on a machine in New York. Location 1000 for the server is a machine in San Francisco. It's a different machine. Those are two different memory cells. They're not the same one. So a lot of programming language mechanisms that you're familiar with from previous classes, which depend on a shared address space, do not work. So the two simplest cases are call by reference, where you pass a pointer rather than sending the whole object. Sending pointers does not make sense in the distributed systems case. The second example is the use of global variables. You have learned now from previous classes, if there's some big data structure, a giant B tree that you've constructed, you don't ship it around, you merely pass a pointer to it. So you make it a global variable. Everybody who operates on it knows this is the shared variable. It occupies one big hunk of memory on heap somewhere, and everyone uses it. This doesn't work in the distributed systems case. So those are only two examples. There are many, many subtler examples, right? Up-level addressing, the use of procedure parameters, etc. But if you think of global variables and call by reference as kind of the two most obvious examples, you have got most of the cases that happen. So that's one way in which, no matter how hard you try, local and remote are never going to be the same. The second source of complexity is delayed binding.
There's a question on track.
Yes?
This is about the previous slide. It's asking what does it mean by synchronous transfer of control?
Okay, hold on. Let me show the previous slide so that people can. Okay, is this the slide?
Yes.
And then what is the question?
The student asked, what does it mean by synchronous transfer of control?
Oh, synchronous transfer of control is the fact that either the caller is executing or the callee, but never both. In the case of the local, because the line is horizontal, almost instantaneously, the caller stops, and with no delay, the callee begins execution. So during that dotted line, there's no time, it's zero time. In the distributed case, the caller stops, the packet containing all the information about this procedure call slowly makes its way through the internet. During that time, the caller is blocked. The callee doesn't even know he has been called. So they're both blocked. So synchronous transfer of control means at most one of the two parties is executing at a time. Neither executing because of communication delay is fine, but there will never be a case where both of them are executing at the same time. And you ask whether that answers the question, or the person can speak up on the audio channel too and ask the question if needed.
Yes. She said thanks.
Okay, fantastic. Any other questions? All right. Onwards. Okay, where were we? Okay, I was talking about delayed binding. So one of the lessons you learned, all of you who are CMU undergraduates, who have taken our undergraduate sequence of courses, have a lot of exposure to the value and importance of compile time checks as opposed to runtime checks. How early in the process of writing a program can you detect an error? If I can detect it very early, then I typically am able to make the fix be much simpler. Now, you all know, all of you have taken these classes know that things like strong typing help push the capture of errors much earlier in the pipeline. So, in general, errors that are caught earlier in the pipeline are simpler. Unfortunately, in the case of distributed systems, there are some errors you cannot push further back. The reason is, by its very definition, the server can only be communicated with at runtime. In programming languages, in a static case, in the local case, I can use what is called static linking, which means all of the dynamic references made by a program can be resolved before you start execution. And so a statically linked executable will never have any errors involving a missing function, because you would have already discovered that long ago. That discovery is not possible with distributed systems. The reason is the whole point of a distributed system is to communicate with the server, which may not have been in existence 1 second ago. It just came up. Okay? So delayed binding is one source of complexity. Another has to do with failure independence. In the local case, procedure A calls procedure B. They're both running on the same machine. If the machine dies, both A and B also die. So A is never around to attend B's funeral. And B is never around to attend A's funeral. There's no eulogy that we can give about how great B was, and we are so sad about the passing, right? Because you died too. So shared fate is the nature of failures in the local case. The distributed case, well, the server in San Francisco can die, but the server in New York is running quite happily, and vice versa. It's also possible that the New York server is happily running, the San Francisco server is happily running, but they can't talk to each other because the network is broken. So the range of failures is significantly larger and more complicated, and failure independence, I would say, accounts for, as a rule of thumb, roughly half of the complexity of distributed systems comes from just this one point. Okay? How to make things work. Much later in this class, you're going to learn about paxos, about two-phase commit. In all those cases, the easy case is trivial. All of the complexity comes because of failure independence. Okay? And last but not least, yes?
The student asked, first, is static linking only something we can do to files that aren't used on a distributed network?
So let me repeat the question for the benefit of everybody on Zoom. The question is static linking only doable in the local case? And then what is the other half of the question?
Yeah, this is the question.
Yes, static linking is only possible in the local case, because by definition, the two halves of a client-server pair can only be put together at runtime. There is no compile time. I can compile a fantastic procedure involving the server in New York, the client in New York, and the server in San Francisco, but it's a pack of lies, because at runtime, when you make the call, if there's a power outage in San Francisco and the server just died, what are you going to do? Your promise isn't worth the paper on which it was written. So static linking is only possible in the case of a single site. Okay, any other questions?
He also asked, how exactly failure independence? Sorry, can you rephrase your question?
Feel free to also just speak on the audio channel if it's easier.
Yeah, can I? Sorry, hi. I'm the one who asked the question. So we are looking at failure independence, and we're saying that that's a limitation of RPC. But I'm not exactly seeing how failure independence is a limitation. It sounds like something that's actually kind of good.
Okay, so your question is, how is independence of failures a bad thing? You would think of independence of failures as a good thing. That's your point?
Exactly, yes.
Well, you've seen the cartoon, right? Of the three monkeys. Hear no evil, speak no evil, see no evil. You've seen that cartoon?
Yeah, sure.
Okay. This is the point. In the case of failure dependence, the two pieces of code will never see the other one die. I don't need to write any code to handle that exception. It'll never happen. Because every time the other guy dies, I'm dead too. So failure dependence means elimination of a lot of cases that will never occur. So my code complexity is simpler. With failure independence, I can see now that the other guy is dead. And I have to now have code to say, when I made the remote procedure call, while it was working on this code, or before it received my request, if the other party dies, then here's what I have to do. It's an exception. I have to write an exception handler for it. Does that answer your question?
It does, yeah. It's kind of like the metaphor with great power comes great responsibility. Throw another one in there. I think I get it.
Right. So the critical insight here, the critical insight to keep in mind is independence gives you power, just like parallelism gives you power. But that power comes at a cost, and the cost is complexity. And just as synchronous transfer of control deliberately simplified the story so that you didn't have to deal with many, many cases, in this case, alas, the opposite problem is true. I cannot legislate away independence of failure. In the real world, that's what happens. And so code, whether you like it or not, the code you write has to deal with it. If you don't explicitly deal with it, then the logic in your code is implicitly dealing with it in an unspecified way. Okay. I think this is a last point here is security. In the local case, typically you're calling another procedure within your same address space. Therefore, you're typically operating at that same trust level. In a distributed system, this is not true. Amazon is selling things, its web server. How does it know that this client who's asking for, ship me 10 widgets? It has no clue. It has to go through an explicit security check and enforce security to make sure the payment is going to happen, that this is a legitimate requester, et cetera, et cetera, et cetera. So many steps involving security that are trivial in the local case, shared address space case, become more onerous in the distributed case. So I'm going to stop here and I'm going to let Babu take over. So Babu, while you're setting up, I will answer the question. Go ahead, Chife.
You can walk path to explain why communication is non-transitive as shown in this slide.
Communication is non-transitive. The reason has to do with the nature of networking. Today's networks are store and forward networks. In other words, when your packet travels from Pittsburgh to San Francisco, it actually goes through many, many, many intermediate internet routers. Every single one of them has a routing table, which says, if the packet is intended for San Francisco, the next hop should be this router. If the packet is intended for Toronto, this other router is the best choice. So there's a routing table that at each decentralized routing table. One source of non-transitive communication is bugs in the routing table. It is possible very easily to set up a set of routing tables so that the property described here is true. There's a completely different second reason, which has to do with wireless networks. There, the physics of the situation may be A and B are able to talk to each other, and A and C are able to talk to each other, but between B and C is a big obstacle, and therefore they're not able to talk to each other, right? So either biological reasons or physical reasons, this is possible. Right, Babu, all yours.
Okay, great. Thank you, Satya. All right, so.
We'll have to defer it to office hours.
All right, great. So.
Go ahead.
All right. Yes, so we're going to start our projects for this course right away. The semester is very tight this year. I think spring break is early this year, right?
Yeah.
So
14 weeks as opposed to previous years when you had 15 weeks.
So yes, so we'll have to start projects right away. And so our first project is going to be on remote procedure calls. Yes, I know we haven't quite covered the whole topic yet, but we will be finished with that in the next couple of lectures anyway, so you'll have all the information you need to actually get this project done. So the main task is for you to actually build a remote procedure call system, okay? And the idea behind this is to allow you to do a particular service, a file system service. Basically, you're going to create a remote file system that allows standard operations like open, read, write, close, all the usual things you can do in a file, as well as a couple extra ones we made into just make it a little bit more challenging for you. And you're going to write basically a small library that lets you do these remote procedures, but in a remote way, right? And we're going to require you to do multiple clients, all the kind of good stuff that you would expect from a serious service. The interesting twist on this project is that we really want to push on this one aspect of remote procedure calls, right? The one key aspect of remote procedure calls is it provides an abstraction that looks like a normal local procedure call, right? And we want to push that as much as we possibly can. So to that end, we want a system that mimics the local procedure so well that a given program that doesn't even know anything about remote procedures, doesn't know anything about the fact that it's doing anything in a remote file server, can actually use your RPC system, right? We're going to make it completely transparent. So how are we going to do this, right? So recall from 213 or the equivalent class, when you actually run a program, let's say like cat, right? You're actually running a compiled binary that actually does a bunch of calls, right? It does an open call on the file, it does some reads to read some data from it, and then does a close, right? But it's important to note that these are dynamically linked programs, right? So although it uses open, close, read, it doesn't actually have the implementation of these functions in the binary itself. Instead, the actual implementation exists in another file, a different binary, a library that actually has the implementation. This is the standard C library. And this is often called a shared library in Unix world, or the DLL, dynamic link library in the Windows world, but it's the same thing. You have basically all these common functions pre-compiled in a separate binary that the particular program can use through something called dynamic linking. Basically, when you run cat, the loader will load the program cat and make these little connections. Basically does a dynamic linking so that every time open is called, it actually calls the open in libc.so, right? So this is normally what happens, and these are all local procedure calls, right? So what we're going to be able to do is we want to be able to have a RPC system that is so good, we can take this unmodified binary cat program and make it work with your remote procedure calls. And the way to do that is by using something called interposition. Basically, what we're going to say is when we start the cat program, by putting that little environment variable saying that we're going to preload a different library. We're going to say that when we run the cat program, instead of having that open link to the open in libc.so, we're going to have it link instead to the open in mylib.so. And so the mylib.so is going to get precedence over the libc.so. So now when open gets called, it actually calls this version of open. Okay? Now note that the actual cat program has not been changed at all. It has no clue. It's just calling open. It just happens to be that open is redirected to something else. What we're going to do for this project is you're going to write your RPC library like this library here, such that when we run cat, we're going to use your version of open, your version of close, your version of read, instead of the standard ones. And your versions are actually going to do the remote procedure call. So when it calls open, it doesn't do an open, local open. It instead does the messaging to the server and does the remote side open. So basically, you're replacing your standard procedures, local procedures, with your RPC versions, right? So that's what this project is going to be about. So the things you really need to review from 213 of similar classes are, these are kind of things that you probably have touched upon in other classes, but you really should review. Things like what the C file operations are like, right? Since those are going to be heavily used here. How to do networking in C, and how to deal with multiprocessing. Those are all important things for this project. And this is why 213 is a core requirement for this class, not optional. So this is a fairly substantial project. We'll have about 3 weeks to cover everything. But we'll have 2 checkpoints and a final checkpoint for this project. The first checkpoint is actually going to be due this Friday. It's pretty quick, but we really want you to get started. The first checkpoint is not actual RPC. It's actually more of a light introduction to make sure you understand what the file operations in C are and that you can get networking working, right? That's about it. And then as an example, how to do the interposition. The starter code that we provide will give you examples of how to do all of this. You just have to kind of extend it for our first checkpoint. So please get started on that right away. The other 2 checkpoints are due the following Friday and the Friday after that. But those are going to be substantially more work than what's in checkpoint 1. So get started as early as you can on all of the checkpoints, okay? Please don't wait until checkpoint 2 is due to start checkpoint 3. If you can do it earlier because you will need the time. A little bit about the logistics for this. In this course, we have no group projects. So all of the projects are actually designed, even though they sound very, very substantial, they're actually something that people, individuals can do very easily, okay? So that's why we've designed this. So we have no group projects. And for a class this size, it's actually pretty good because we'll always have issues of people dropping the course. If you had a partner that drops, it's just so many problems we can run into. So all individual projects. For project 1, everything is going to be written in C. The whole project is a C-based project. Projects 2, 3, and 4 are mostly going to be in Java, even though, at least for project 2, a good C background is still going to be needed. For this project, you can use standard C libraries and things like that, but you can't use any libraries that actually do RPCs themselves. So you can't use an RPC library since you're writing one, right? So that wouldn't make sense. Similarly, you can't use serialization, like boost serialization or anything like that. The point of this is an exercise to write your own version. An important point is that we provide a bunch of binary tools, as well as some additional support code. All of those require a 64-bit x86 Linux environment. So for example, you can use any of the Unix servers on campus, unix.andrew.cmu.edu. Should be able to run any of this code. Autolab that we're using for grading also has the same kind of environment. In particular, what we provide will not work on Mac or Windows, okay? Even though you might have a 64-bit environment in Mac, it's not going to run the binaries. Generally, since we're doing network communication, you do have IP addresses, you do have ports that you need to encode. Please don't hard code those. Use the environment variables to do that. The sample code will give you some examples of that as well. That just makes testing a lot easier too. The other thing is, because the Unix at Andrew.cmu is a shared environment, you and some of your classmates may be physically on the same machine at the same time. So please pick random ports so you don't collide with your students when you're running your programs at the same time, right? An important point, it's kind of minor, but it is still important, is that a lot of the grade is based on correctness. So we do check the outputs of programs that we run for testing. So make sure your code doesn't inadvertently add extra output. So you may print some messages, for example, debugging messages. When you hand in your code, don't print those out to standard output, because that'll get mixed in with whatever the binary tool like cat or ls is doing. And the grader is going to say, oh, yeah, the output doesn't match, and you'll fail even though you got everything basically correct, right? So don't put any extraneous output. You can write the standard error for those. That should be okay. And one very important security note: you are building basically a very, very, very simplified file server, right? So, and we have no sense of security or anything on this. So your code could, in theory, allow anyone on the internet to send messages to your service and have them either read or write files to your AFS space on Andrew, right? So be careful with your server. Don't just leave it running. Just run it, test it, and shut it down. Okay, please don't leave it running. It's pretty unlikely, but still, the security hole exists if you use this kind of a project. So that's always something to be aware of. A little bit more on logistics again. We are going to use Autolab for grading. We have, I think, 315 students between those actually registered and those on the wait list right now. So this is an absolute necessity for this class in order to be able to do any grading in reasonable amount of time. So everybody who is who's registered for the course or is on the wait list should have access to the course material on Autolab. In Autolab, you'll find both the Project One handout, which is on Autolab and on the website, but also the starter code that we provide you so that you can download from the project page. Sorry, I did not update the little logo there that should say S22, of course. Each checkpoint will appear as a separate project on Autolab. You should know that, yes, all of those are actually the same project. Just because they have different deadlines, they'll have a different, show up as different assessments. A little bit of note, we do have grace days in this course for projects. We have a total of 5 grace days to use anytime you wish for the entire course. But you can use only up to 2 grace days or late days per checkpoint. And those will be automatically applied. So if for whatever reason you're out sick or something like that and you need to turn checkpoint 2 in a day late, the system will automatically use one of your grace days for that, and you won't be deducted any points. On the other hand, if you had run out of grace days, then it will deduct some percentage of your score for that late day. Remember, the total is 2 grace days or late days. So any assignment can be turned in up to 2 days late with or without penalty, but not more than that. Otherwise, we'll get very, very far behind in grading. Another important point is with Autolab, you have to submit your submission as a gzipped tar file. You must include all your sources and the makefile, and all the sources must be in the root folder with that in that tar file. There will be some parts of the assignment where you need to turn in some write-up, a small write-up, usually a 1 or 2 page write-up. Those designed documents should be in a PDF format to make grading easier. Please don't submit like Word files or any other proprietary document. Please just submit a PDF. Okay, any questions? I think that's all I had. So questions at this point on the projects? Anything on the chat?
asking about some logistics questions, and I've already answered it.
Okay, great. So yes, for everyone, make sure that everyone has access to AFS. The Auto Lab. That's very important. Given that the first deadline is Friday, we want to make sure everybody has their account working. And everybody on either the registered for the course or on the wait list should be on Piazza as well. We made sure everybody had an account. So we have all, as of last night, we had 315 on both. So everybody should be there, but if there isn't, please let us know right away. Satya, do you want to say anything about the wait list? I think since
I've already posted on Piazza.
Okay,
nothing more to say. So keep fingers crossed and be optimistic.
Okay, great. It's good to hear. And of course, remember, make sure you use Piazza and the office hours wisely. Any questions on Piazza, we'll hopefully be able to answer very quickly. And with projects already starting, I think we'll be ready to answer your questions right away. So please get started early. Thank you.
Okay. Next class.